Welcome to the next set of video notes for Intro to Statistics at CCD. We are going to finish Module 4 today in these notes. So the fifth part, we're going to look at standard deviation and the empirical rule. And then there is something that I've tacked on at the end that I just don't feel our textbook introduces early enough. So we're going to start by looking at standard deviation. Standard deviation, let's give you guys a bit of a definition real quick. Oh, there we go. Standard deviation measures the average distance that the data is from the mean. So it's an average, but it's also a measure of spread. It's going to tell us how spread out our data is in relation to the mean. So we're going to look at the equations on how to calculate the standard deviation, starting with the sample standard deviation. The symbol for sample standard deviation is going to be a lowercase s. And then that equation, we're going to take the square root. We're going to sum each x value minus the mean squared, and we're going to divide that by n minus 1. And the good thing is we're going to go through this once by hand, and then your calculator actually gives you this value as part of that 1var stats that we were using last week. Okay, so that's the sample standard deviation. Now the population standard deviation equation is just a little bit different. So the symbol for that is going to be a curly Q O, almost like a cursive O. This is sigma. This is a lowercase sigma. So again, remember, standard letters that we see every day represent samples. Greek letters represent population values. And the population standard deviation is also going to be found by taking the square root, adding up each x value minus the mean squared. But this time we're going to divide it by just capital N, which remember is the population size. So that's the biggest difference between these two equations, is for the sample, we divide by n minus 1. For the population, we divide by the full population size. There is a very good explanation for why we do these. If you would like to look it up, you can look at the proof. Wikipedia actually has a pretty good article on that, or you can just take my word for it. Most people do. All right. So these are the two equations. We're going to focus on the sample standard deviation because that's the one that we're going to see more in this course as opposed to the population standard deviation, because most of the time we don't know what this value is right here. We don't know what the population size is going to be. So let's go ahead and do an example of calculating the sample standard deviation by hand. So the first thing I want to do is I want to fill in this table that I've created to help me kind of manage everything I have to do with my data values. So I have 4 data values that we're going to use. I have 63, 88, 77, and 68. Now the next thing I need to do is I need to go calculate the sample mean, because up here looking at the equation, we need to take each of these data values and subtract the mean. So I'm going to calculate the sample mean, which happens to be 74. So I'm going to fill in 74 all the way down. This is just so that visually I can see exactly what I'm having to do from one column of my table to the next. Okay, so now we want to find the deviation about the mean, or we want to find how far away is each data value from the mean. So we're going to do that by taking each data value and subtracting the mean. So 68 minus 74. Oh, I'm sorry, 63 minus 74. Getting ahead of myself. Let's fix that. 63 minus 74, which is negative 11. 88 minus 74, which is 14. 77 minus 74 is 3. And 68 minus 74 is negative 6. All right, So remember up at the top, I said that a standard deviation is the average distance that our data is from the mean. So I found how far away each data value is from the mean. So wouldn't it make sense for me to just find the average now? Add up these four numbers, -11, 14, 3, and -6, and divide by 4. That's how we calculate an average, right? Well, go ahead and add up these numbers. And when you do, you will find that the sum of these four numbers, the sum of the deviations, is equal to 0. And that will always happen, no matter what your data looks like, no matter whether it's symmetric or skewed. When you add up each of the deviations, you get 0. And remember, anything divided by 0, or 0 divided by anything, is always going to be 0. So taking this and dividing by 4 doesn't really tell us anything about the average distance that our data is from the mean. So to get around that, what we end up doing is we end up squaring each of these deviations. Remember, squaring is when you take the number and you multiply it by itself. And so that gets rid of all of these negatives. So -11 squared is 121. 14 squared is 196. 3 squared is 9. And -6 squared is 36. And it is important that at least these negative numbers, you put them in parentheses before you plug it into your calculator. Because if I didn't have the parentheses around the -11, my calculator would have told me that -11 squared is -121. But that's not the case. Okay, so now once we finish this table, we are up to this part of the equation. So we've done everything that I have boxed so far. So we took each data value, we subtracted the mean, and then we squared it. So now the next thing we need to do is we need to sum or add up all of those deviations squared. So I'm going to come back down here and I'm going to add up these four numbers. So 121 plus 196 plus 9 plus 36. And I get 362. All right, so now we've taken the sum of everything. So now we're up to this part. So the next thing I'm going to do is I'm going to divide everything by n minus 1. So I have 362. And I'm going to divide that by my lowercase n, which remember is our sample size. So that was 4, but I need to subtract 1 from it. So I'm going to take 362 and I'm going to divide that by 3. And that gives me 120.6667. I would like you to use the decimals all the way through to the end. So don't round until you get to your final answer. And that's what I'm doing in my calculator. All right, so now going back to our equation, where are we at? We took the deviations, we squared the deviations, we took the sum of all of those, and now we've divided by n minus 1. So now at this point, we have done everything inside the square root. So the last thing we need to do is take the square root. So I'm going to do 120.6667. Again, use all the decimals until you get to the end. And I'm going to take the square root of that. Okay. And I get 10.9848. And that is my sample standard deviation. So S equals 10.9848. So that means on average, I didn't write it. S equals 10.9848. There we go. So that means on average, my data is 10.9848 units away from the mean. So if these were, let's see what these numbers are. Let's say these are, oh, it does say exam scores. So this may be like the percentage that someone got on an exam, or the number of points that they got on the exam. So on average, these 4 students are scoring 10.9848 points away from the mean in either direction. They're 10 points above the mean on average. They're 10 points below the mean on average. It doesn't mean that each value is exactly 10 points away, because as we saw up here with these deviations, they all had a different distance, but this is the average of those distances. Okay? And then this last step, just so you know, the square root that we took was to undo the squaring that we did up here in the last column of the table, because we don't want this stuff in terms of points squared or units squared. We want them just in terms of the unit itself that we're looking at. So that's why we have to take the square root at the end. So this is how you calculate the sample standard deviation. Like I said, you will be able to use your calculator to do that. I believe there may be a question in next week's discussion where I have you do this, but it's for a small manageable data set like this one here. I'm not going to ever have you do this table with a data set with more than, I think 8 numbers is the biggest I've ever given, because it's a lot of steps and there's a lot of places where you could go wrong with this. So I want to make sure that we're seeing how to do it, but also knowing that there's technology that'll help us do this faster. So now let's look at a way to interpret standard deviation. So what I have here is I have 2 histograms. They represent IQ scores at 2 different universities. One important thing is both of these graphs have the same mean. So University A and University B, they both have the same mean of 100 for their IQ scores, but their standard deviations are very different. So the standard deviation of University A is 16.2, and the standard deviation of University B is 8.1. So seeing the values of the standard deviations and seeing what the histograms look like, what does this mean? Well, it means that the data for University A is more spread out than University B. And that's something that will always be true. If you are comparing standard deviations between 2 different data sets, the standard deviation that is larger represents the data that's more spread out. And we can see that in this graph here. Okay, University A has a small score all the way down here at 55, whereas University B's smallest score is over here at 85. And then on the high end, University A goes all the way up to 145, whereas University B stops at 120. Okay, so the range for these scores is a lot different. University B has a much smaller range than University A, and that's reflected in their standard deviations. Okay. So that is what we're seeing when we're looking at the differences between standard deviations of our data set. So now another measure of spread that we have is the variance. So the variance, we're not going to look at the equation for it. I'm just going to give you guys the notation. Let's do it in black. The sample variance notation is S squared. And the population variance notation is sigma squared. Because the variance, very simply put, is the standard deviation squared. Okay, so it's the step before we took the square root at the end. So we're going to find the variance of the standard deviations from example 2. Now we aren't going to do a lot with variance in this course, but if you were to move on and take more statistics course, you would have a lot more uses for variance. All right, so example 2 was the University A, University B data that we had just right here. So we're going to find the variance of University A. So let's do University A in blue. So University A, we're going to call this a sample because I don't know if it's a population. Okay, and its standard deviation was 16.2. So to find the variance, I'm just going to take 16.2 and I'm going to square it. So I'm going to multiply it by itself, and that gives me 262.44. And then I'm going to do the same thing with University B, which had a standard deviation of 8.1. So let's do green. So B, their S squared is going to be 8.1 squared, which is going to be 65.61. And that is how we find variance. And that's all I'm going to ask you to do with variance. I'm not even going to ask you to interpret variance because it gets a little bit funky because it is in terms of units squared. But just know it is another way to measure how far away the data is from the mean. And it's simply found by taking the standard deviation and squaring it. All right, so moving on. The empirical rule, I think the empirical rule is super fun. I love teaching the empirical rule, and I love doing problems with the empirical rule. So the empirical rule only applies to data that comes from a bell-shaped distribution. So remember, that means that we drew our histogram, and our histogram appeared to be bell-shaped. So for example, if I come back up here, University A appears to be bell-shaped. University B, not so much. It may be a little bit skewed, but University A, I could draw my curve over this histogram, and it looks pretty bell-shaped. University B's got something weird going on. Definitely not bell-shaped. Okay. So over here, this empirical rule is only going to apply to data that is bell-shaped. And what it says is that approximately, and that's key, it's approximate, approximately 68% of the data will lie within one standard deviation of the mean. Approximately 95% of the data will lie within two standard deviations of the mean, and approximately 99.7% of the data will lie within three standard deviations of the mean. So what does that actually mean? Well, if I come down here to this chart, it means my mean is in the middle. Remember, we have our mean in the middle. If we take our mean and we add one standard deviation to it and subtract one standard deviation from it, 68% of our data is going to be between those two numbers. And then if we go out again and we take two standard deviations away from the mean and two standard deviations added to the mean, 95% of our data is going to be within those two numbers. And lastly, three standard deviations below the mean to three standard deviations above the mean, 99.7% of our data is going to be within those two numbers. Okay? We are going to look later on in the semester at exactly how these values were found. If any of you have taken calculus, I love when I have students who take calculus because I get to tell them this. These percentages are found using integrals. That's all I'm going to say on that. You don't have to have taken calculus. It's just fun when you have. I think calculus is fun. So let's go ahead and look at how we can use this information with an actual data set. So I have right here example 4, using a mean of 100 and a standard deviation of 15, use the empirical rule to answer the following questions. What percentage of students have an IQ score within 3 standard deviations of the mean? All right, so the first thing I want to do is I want to draw my bell curve, and I want to label this mu plus 1, mu plus 1 standard deviation, mu plus 2 standard deviations, and so on. So I'm going to do that over here kind of off to the side a little bit. So here's my curve. I'm going to draw a line underneath it. Maybe. There we go, that's better. And I'm going to start labeling things. So I'm going to put my mean here. And the problem says that the mean is 100. So I'm going to put in a 100 right here. And then I'm going to start going out with the standard deviation. So one standard deviation above the mean will be about here. So that means I'm going to take 100 and I'm going to add 15 to it. So that gives me 115. And then below the mean, I'm going to take 100 minus 15, which is 85. Okay, and it didn't write everything down again. 85, 115. All right. Now I'm going to go 2 standard deviations out. So I'm going to be here. I'm going to take 115 and I'm going to add 15 to it again. So I'm going another 15 out plus 15. I'm just trying to squeeze everything in here so I don't run out of room, which is 130. And then 85 minus 15 is going to be 70. It's probably not going to write everything. 130, 70. And then finally, 3 standard deviations out. I'm just going to write the numbers. So we had 130 plus 15 is going to be 145. And then 70 minus 15 is going to be 55. I don't know why it's doing this. 145, 55. Close enough. All right, so now I can see all of the values that I have for this example. So now the first question said the percentage of students who have an IQ score within 3 standard deviations of the mean. So it's not asking me for the numbers that are here. It's asking me for what percent of students are going to be within 3 standard deviations of the mean. Well, if I come back up here to my in general graph that I have, from 3 standard deviations below to 3 standard deviations above, that contains 99.7% of my data. So we're looking from here to here. So I come up and here we see 99.7%. So the answer to this first question is 99.7% of students have an IQ score within 3 standard deviations of the mean. So moving down, so the percentage of students who have an IQ score between 70 and 130. So now I do need the chart that I've drawn. So I have 70 to 130. Well, 70 is 2 standard deviations below the mean, and 130 is 2 standard deviations above the mean. So from 2 below to 2 above, that is 95% of my data. So I'm going to come in here and I'm going to say 95%. And then the last question is the number or the percentage of students who have an IQ score above 115. So 115 is right here. And I want to know what percent of students have an IQ score above that. So what I'm going to do to find that value is I'm going to come up here. So that's 1 standard deviation above the mean. So we're looking at this guy right here, and we're looking at everything above it. So notice I have these percentages inside the curve, 13.5, 2.35, and 0.15. Okay, these represent the percent of scores between the standard deviations. So to find the answer to this guy, I'm going to take 13.5 plus 2.35 plus 0.15, and that will tell me overall what percent of students have an IQ score above the 115 that I'm interested in. So I'm going to come back down here, and we have 13.5 plus 2.35 plus 0.15, and that equals 16%. So we can use this whenever we have values that fall directly on each of these standard deviations, and then we can use this guy and all of the values within it to find the percent of students or the percent of individuals within our data that fall between 2 numbers. Okay. But what if, or nope, I'm sorry, I'm jumping ahead of myself. So that's the empirical rule. Okay, you will need to know this graph right here for your exam with the percentages and everything. So the last thing we're going to talk about in these notes, this is something that your book doesn't cover until much later. And I did that last semester and I didn't like it because it became a little overwhelming. So I'm going to introduce them now. We're not going to do a whole lot with them, okay? But we're going to go ahead and take a look at z-scores. So a z-score tells us exactly how many standard deviations from the mean a data value is. So when we were up here, we knew that 115 is exactly 1 standard deviation above the mean. 130 is 2 standard deviations above the mean. But what if we have a data value that doesn't land at exactly one of these points? What if I have the data value 114? How many standard deviations away from the mean is the data value 114? It's not 1 standard deviation away from the mean because that's 115. So what we have is we have a formula, a z-score formula, that will calculate that for us. So our z-score formula, so this z stands for z-score. Let's switch colors right here. So this is the z-score formula. What we're going to do is we're going to take our data value, we're going to subtract off the mean, so we're going to find how far away that data value is from the mean, and then we're going to divide that by the standard deviation. And yes, I am using parameters in this equation right now, so I'm using mu and sigma as opposed to x bar and s. There's a reason for that, but we're not going to get into that until much later. So just go with it for right now. Okay, it's not going to make a big difference in how you calculate this stuff. So let's go ahead and look at how we calculate this. So we're going to use a mean of 100 and a standard deviation of 15 again. And we're going to calculate the z-score for a few numbers. So we're going to find out exactly how many standard deviations away from the mean are these numbers. So the first one we're going to look at is x equals 90. So I'm going to start by writing in, so z equals, for x I'm going to plug in 90, minus my mean, which I was told is 100, divided by the standard deviation, which I've been told is 15. So now I'm going to do the math. So 90 minus 100 is negative 10 over 15. So negative 10 over 15 is negative 0.6667. So what this tells me is that the data value 90 is 0.6667 units below the mean. I'm sorry, not units. 0.6667 standard deviations below the mean. So it's about 2/3 of a standard deviation below the mean. All right, so now let's do the same thing, but with the data value 125. So z equals 125 minus 100 divided by 15. So 125 minus 100 is 25 over 15. 25 over 15 is 1.6667. So the data value 125 is 1.6667 standard deviations above the mean, or about 1 2/3 of a standard deviation above the mean. So if I come back up here to this graph that I had drawn, he's somewhere, so here's 1 standard deviation above the mean right here. Okay, this is 1 standard deviation above the mean. This is 2 standard deviations above the mean. So this guy is going to be somewhere like right here. Okay, and we can see that. This is 115, this is 130, and then our graph was looking at the number 125. So he's somewhere in between these two numbers, and we can say that he's now about 1 2/3 of a standard deviation above the mean. And then finally, we're going to look at x equals 101. So z equals 101 minus 100 divided by 15. So 101 minus 100 is 1 over 15. And we do want to make sure that we're always turning these into those decimals. So 0.0667. So that is the number of standard deviations above the mean for a data value of 101. Okay, and then we could also work backwards. And if I told you that you have a data value that's 2.5 standard deviations above the mean, what is that data value equal to? Okay, so if I had a question like that, you would plug in 2.5 equals x minus 100 divided by 15. And you would need to then solve for x. Okay. So let's go back up to the top and we'll review everything. So we were looking at standard deviation first. We focused more on sample standard deviation, went through how to do it by hand. Talked about how to interpret standard deviations. We looked at the variance, which remembers just the standard deviation squared. We looked at the empirical rule. And then finally, we looked at calculating z-scores. So that is it for Module 4. And the next couple of notes will be up